The facility is the synthesis hub to about a dozen personnel, including research staff, students, and graduate students. Specialized synthesis is conducted in the facility, centered around an instrument purchased by Ultrasafe Nuclear Corporation known as a pulsed electric current sintering furnace, or colloquially, spark plasma sintering. This instrument conducts rapid sintering of ceramics, which has a venerable and ancient history of how pottery and cookware were developed. Powders are carefully selected, mixed, and compacted, and fired to form a part. During that firing, heat is applied, so atoms move along specifically defined paths, which may or may not close the gaps between the particles. The final product is usually a dense and hard material, such as a plate or a cylinder, with the original powder surfaces found as grains within the material. This process is essentially how nuclear fuels are fabricated in the US civilian reactor fleet. Uranium dioxide powder is mixed with other compounds, compacted, and fired to form cylindrical pellets with known grain sizes. This laboratory is focused on synthesis, so the fired product is analyzed and tested with one of the university's extensive characterization facilities at the Joint Institute for Advanced Materials or the Materials Science and Engineering Department. The contemporary engineering of pottery to its current form is focused on the development of new compositions of ceramics and different morphologies to obtain different properties. Specifically, this instrument sinters rapidly because the powder is compacted within a graphite die. The graphite die is connected to an electrical circuit, which rapidly heats the ceramic powder to a temperature where atoms can move. In addition, a high pressure is applied, which can assist in closing gaps between the powder particles. Unlike a conventional furnace or an oven, heating is generated within or adjacent to the part, so the glow on the walls is actually cool at about 200 degrees Celsius, while the part itself is at about 1800 degrees Celsius, or 3300 Fahrenheit. The importance of sealing the myriad gaps between metal and ceramic powders is a requirement of robustness and safety of nuclear fuels and materials. Our compositions include molybdenum, tungsten, and many carbides such as silicon and titanium carbide. These compositions are also found in rocket nozzle liners, armor plating, and heating elements. The reason for selecting these materials is that they are ideal for encapsulating nuclear fuels, permitting a higher operating temperature and increasing the energy density that a society can use.